Hello, good evening. Shall we start, sir? Hello, Anurag, sir.
Yes, you
Yes,
can
sir.
go ahead and start.
Okay. Good evening to all, and it is with immense pleasure to welcome you all to the second day of the AICT sponsor ATAL 6-day online faculty development program on transforming industries with AI, deep learning breakthroughs, and real-world applications, organized by Department of Computer Science and Engineering, SRM Institute of Science and Technology, Ramapuram, Chennai. It is distinct honor to introduce our esteemed resource person for the day 2, session 3 of this faculty development program. We are privileged to have with us Dr. Anurag Nagar, an associate professor of instruction in the Department of Computer Science at the University of Texas at Dallas. Dr. Nagar is a distinguished academician and researcher with extensive experience in computer science education. At the University of Texas at Dallas, he has been instrumental in shaping the curriculum and mentoring students in various areas of computer science. In addition to his research, Dr. Nagar is known for his excellence in teaching. He has taught courses such as machine learning, where he introduces students to the study of computer systems that improve their performance over time. Dr. Nagar has also been actively involved in the academic community, participating in events like the 2018 Data Science Conference hosted by UT Dallas Computer Science Department. His dedication to teaching and research excellence has significantly contributed to the advancement of computer science education. Dr. Nagar's insights into the practical applications of AI and deep learning are invaluable, and we are fortunate to have him to share his expertise with us today. Please join me in extending a warm welcome to Dr. Anurag Nagar, sir. Welcome you, sir.
Thank you. Thank you. It's a great pleasure to be here. And
Okay.
can I share
I
my
will
screen?
make you as host there, then you will share your.
I want to share my screen with you. So
Yes,
can I
sir. And you
see
have to
you?
share your screen now.
Okay, so let me do that. So are you able to see my PowerPoint presentation?
Yes, sir. Yes.
Okay. So, good afternoon, everybody. Although it is morning here, I'm in Dallas, Texas, and it is morning here. But for most of you, it may be evening or afternoon. So, good afternoon to everybody. And today's topic would be convolution neural networks. So, how many of you are familiar with convolution neural networks, or have you heard of something called convolution neural network? So you can simply type it in the chat if you have ever heard of convolution neural network. Okay. So to understand convolution neural network, convolution neural networks are a type of neural networks. So, we first have to kind of talk to you a little bit about what are neural networks. And I'm sure many of you know what is a neural network, but just to recap what is a neural network, and then we will go to why is the need for a convolution neural network. So we will talk about, what is the neural network first, and then why a plain neural network cannot do the task that we are about to do, and why we need a specialized type of a neural network called convolution neural network. So we'll talk about that. So let me start my presentation, and then we'll talk more. So let's go ahead and see this. So, what is a neural network? Neural network is a supervised machine learning algorithm, and you have to understand what is a supervised machine learning algorithm that is used for predictive analysis. So, you have to understand that a plain neural network, which is what we said, which is a plain neural network is a supervised machine learning algorithm used for predictive analysis. And so, what a little bit more about what is a neural network? Neural network is a network of neurons working together in an interconnected fashion. So, you have to understand, and I will give you a visual image of that, which we will see later on, that it is a network of neurons working together in an interconnected fashion. It is, if you want to understand it, it is kind of like the human brain. So neural network is kind of like the brain. It is, it like tries to mimic the behavior of a human brain, and we will give you some more examples of how a neural network is like the human brain. So neurons are arranged in the form of layers. So we will talk about layers, and we will see that how in a neural network you will see layers of neurons arranged on top of each other. It tries to mimic the human brain behavior. So the scientists, when they were trying to construct a neural network, they wanted to develop a machine learning algorithm that is resembles a human brain. And neural network is one of the most widely used machine learning algorithm, and that is what a neural network is. So going forward a little bit and taking to the next slide. This is what a neural network is. So as I said, this is neurons. These are all neurons. These units are all called neurons. Now what happens is these neurons are arranged in the form of layer. This is called the input layer. This is the input layer. This is called the hidden layer. And you can have as many hidden layers as you possibly want. That is part of the design. So this is a hidden layer, and you can have one or more or whatever number of hidden layers you want, and this is called the output layer. So you have these type of neurons arranged in the form of layers, one on top of each other, and you can see that it is up to you as a designer to add how many neurons you want. So it doesn't have to be two. In this example, there are two, but you could have 100 such things. In this example, the hidden layer one has three, but you don't have to have three. You can have 100. You can have as many as you want. And you can have, as many layers, as many neurons as you want, and they are connected. The most important thing is they are connected, and these are called connections, and you can see all these connections are there, and they are together trying to solve a predictive problem. So they are trying to, we are training this neural network to solve a sort of a predictive problem. Now, that's great. You can have all these things. You can have you can train this machine, and this is a machine actually. You can train this machine to do a predictive problem for us. For example, you can train it to predict the weather, that or you can train it to predict the stock market, or you can train it to predict how a student will perform in a class. So it is excuse me. So it is up to you to train this neural network to for the given task. Now let me ask you a question, that what are the training parameters in this neural network? Which means what are the training, what changes during the training? You do the training. So what are the training parameters in the neural network? Can somebody answer this question? Yeah, Miss Pooja Soni is giving the correct answer, and maybe somebody else can also tell us what is the training. When training happens, what changes during the training? So what happens is you see these connections. You see these connections all of these connections have a weight associated with it. So what happens is these weights, which are these, if I will show you a real example later on, and these weights, these connections have some weights on them. So during the training process, some weights get larger, some weights get smaller, and that is how we train this machine. So the basic what we do as a machine learning scientist is we train this network. So we train this network to do some sort of a prediction. And when the training happens, we compare the prediction with the true value. The true value is the actual value. For example, the true value is tomorrow's temperature will be 18 degrees Celsius, but maybe the prediction is saying 30. The prediction is wrong. So, based on the prediction and the true value, we compute the loss. The loss means the error. And based on the error, we retrain the weights. So, based on the error or the loss, we retrain the weights, and maybe the second time it is better. It becomes, 23. And then we still have an error, and then we use the error to re-update the weights, and maybe the next time it becomes closer to 18 point, 3. And then we retrain it and we retrain it until the error is low enough. So maybe now the next time the prediction is 18.001, and that means, or 001, that means now the prediction is coming close to the true value. So that is the process in which we train the weights of the neural network to achieve our objective. So this is what a plain neural network is. You have to emphasize that this is a plain neural network. It is not a convolution network, it is a plain neural network. Now I'm going to try to tell you today is why a plain neural network is not, it cannot do very big things, or whatever. If we are trying to do, if we are trying to work with images, or if we are trying to work with video data, or if we are trying to work with some other data, why a plain neural network may not be the best choice, and why we may have to do a specialized neural network which is called a convolution neural network. So that is the topic for today. So the first point of this lecture is to try to convince you that a plain neural network is okay if you are trying to predict the weather, maybe, or if you are trying to predict something simple. But when you are trying to predict something more complicated, like you want to identify objects in an image, or if you want to identify, or if you want to generate a caption for a video, or if you want to do some sort of, you are doing on Instagram and you want to identify objects in Instagram, why plain neural network may not be the best choice. We will talk about that. Okay, let's go to the next slide. What are the applications of neural networks? One of the advantages of neural networks, and it doesn't, I'm not using the word plane or anything, I'm just using neural networks. One of the advantages of neural network is they are known as universal learners. So neural networks can learn anything that you give them. In fact, there is a theorem that is there which is called, universal learning theorem. That means a neural network can learn any task. That is why it is called a universal learner. Now, you have to add some prefix, what type of neural network, but I'm just using the word neural network. So they can learn to represent any type of data. In fact, if you, how many of you have used Chat GPT? How many of you have used Chat GPT or generative AI? You use that on a daily basis. Um, So if you have used Chat GPT or generative AI, even that is using a neural network. It could be using a transformer neural network. But any type of neural network that you use is any type of modern algorithm that you use is using some neural network. Okay, so that is the neural network. Now you have to understand this is a general thing that I'm saying, that training a neural network involves learning by adjusting the weights associated with the connections between neurons. So training process is learning the best set of weights that are there on each neuron, and that is very important, and that's kind of very important thing to understand. Now I know you might know this, or some of you may have experience with this. I would like to give you an example of what training a neural network is all about before I go into convolution neural network, because convolution neural network is nothing but a specific type of a neural network. So what I would like to do is I would like to take you to a simple website called TensorFlow Playground. Now what this website will do is it will take a very simple example and it will try to teach you what training a neural network involves. So what I'm going to do now is I'm going to do something, and I'm going to take you to a website called and I'll share my screen further with you, and I will take you to this I hope everybody can see. So this is a website called TensorFlow Playground. Now, what is this TensorFlow Playground? It is a very simple example of a neural network in your browser. So what you are seeing here is you will simply see that there are two inputs. There is two hidden layers like this, and then there is the output. It's a very simple thing that I'm trying to show you just to tell you the example, just to tell you what a neural network training involves. So I'm just showing you this. Okay, if you have question, you can ask me. But this is, an example. Now, in this example, the dot is the real label. For example, if you see this dot, this object is a blue object. This object is a red object, obviously. Now, the background that is there, the background color is the prediction for the object. So this is the background, and right now the background is blue. That means we are simply saying that the prediction is blue everywhere. But obviously that prediction is wrong. So I'll give you a very simple example that I will run this and the training will start. And what will training involve? Training will involve updating these weights. These weights will be updated, and similarly, when the weight is being updated, the background color will be updated. And I would like the background of the red dots to become red and the background of the blue dots to become blue. So I would like to have to train this neural network to identify the red colors and the blue colors. So let us run this thing, and you will see that very soon it is completed. Very soon the background of the blue dots becomes blue, the background of the red dots becomes red, and it is able to identify the red and the blue dots. Well, there is nothing special about that. It is learned to identify the color. But what I would like to tell you is you will see these weights, that every connection has a weight associated with it. See this? Now, during the training process, these weights have been updated. So you will see that some of the weights have become larger like this, this. some of the weights have become smaller, like this. So it is all about the weights. Now, one of this is important thing because we will learn about convolution network, and convolution network is also about the weights. So you will learn that, it's all about the weights and it is about updating the weights to get the desired result, whatever result you are looking for. So hopefully this makes sense. And is there any question I can answer so far? Because, that is good. So far the story is very simple, that there is a neural network and the neural network has weights and we can use the weights to uh, update the weights and find whatever we want to do. So far the story is very simple. Now you may ask me a question, or I can ask you a question, that why don't we use just a plain neural network throughout? What is, why we need a special type of neural network? Now the story changes a little bit, and now we want to train neural networks to identify, um, for example, we want to train a neural network to identify an image. So let me give you a very simple example and let me tell you what could be the problem. So let me try to give you something to think about, and then we will talk more. So give me 1 minute and I'm going to give you a problem to think about. So let me do something. So hopefully you can still see my screen. Now let me ask you, let me throw a challenge at you. Your challenge is, you are given an image and the image size is 1920 by 1080, and you have to, train a neural network to identify whether the image is of a cat or a dog. That is a very simple thing you have to do. Now, what is the challenge? If you can tell me this, then I'm gonna be kind of happy because it will lead us to the next topic of discussion. That what is the challenge in training a neural network to identify this image? This is the input size, and I want to identify whether it is a dog or a cat. A very simple question. So, what do you think would be the challenge in training a neural network like this? Okay, some of you are giving the very right answer. Um, that, what will be the size of the input layer? If I ask you a simple question, what will be the size of input layer? Well, the size of the input layer will be, you have to take this image and you have to flatten out this image. This is the image and you have to flatten this out. So number of input layer, which means size of input layer, which I'm saying that the number of neurons in input layer is going to be how much? Is going to be 1920 multiplied by 1080, because you have to flatten it out, and that comes to be, some of you have done rough calculation, that comes to be around 2 million. Or if you want to talk, this is 2 million, or if you want to understand it, it is called 20 lakhs. So around 20 lakhs will be the size of the input layer. That is one thing, so input layer size will be around 2 million, which is 20 lakh. Now suppose, but we are not, we are more interested in the number of connections. So suppose, and this is just supposing the hidden layer, the first hidden layer has 100 neurons. So now can you do just a simple calculation to tell me how many connections between input layer and first hidden layer? If you can answer me this question, I'm going to be very happy, because that will take me directly to the topic and I can tell you the topic right away. So what will be the number of connections between the input layer? And I told you number of input layer is 2 million, and first hidden layer has 100 neurons. So you have to connect 2 million to 100. So each of the 2 million is connected to each of the 100 neurons. So how many connections do you see? And if you can tell me the answer, that will be great. Okay. That's what exactly I wanted to hear from you guys, to see your participation. So this means 200 million. And this is where the problem arises. If you have understood this, then you have understood the real need for a specialized neural network, because there are 200 million connections between the input and the first hidden. And this is not even a very large size. This is just a typical image size. So 200 million. Now, to train this neural network, now, this is just between the input and the first. There can be more. So to train this neural network, you have to, you have to find the optimum value of 200 million, or at least 200 million parameters, which is not a very easy task, even with today's computing power. And it leads to all sort of problems. So clearly, a general neural network cannot work for such a task. That is what I wanted to convince to you, that you have some, you have to take a specialized route. So this is where we go to the next part, which is the need for a specialized neural network. So let's go back to our presentation, and then let's talk about, you know, as I said, way too many parameters here. So way too many parameters to train, as I said, 200 million. So this is where we go to the idea of a convolution neural network, which is a specialized type of a neural network that solves this problem. And it solves the problem by not having direct connections. It solves the problem by using something called filters. And I'll tell you what is a filter. Filter is used to identify patterns in the input data. So we are not going to do one by one. Earlier we used to connect everything to everything else like this, and this was the earlier approach. Now we are going to develop filters, and filters are the idea behind convolution neural network. The filters will detect larger patterns in the input data, and these patterns that we detect will be, position invariant, and I will talk to you what is position invariant. But these filters will be used to detect patterns in the input data, And by using these patterns, we will be able to identify the what is the content of the input data. Let's move forward. For example, we can look for patterns in an image. For example, suppose I am developing a bird identifier. So suppose I am developing a bird identifier, then I can develop a filter. For example, this is a filter. Now, what is this filter trying to do? This is called a beak detector. And what is a beak detector? It detects the beak, which is this part in the image. And if I'm able to detect a beak, then that is great. So we are going to look for pattern detectors, and these are pattern detectors. So for example, this image could be 1920 by 1080, but the smaller pattern could be of size 20 by 20. So I'm going to develop many such patterns, and these patterns are going to look for patterns in the original image, and they will answer yes, no, which means whether such a pattern is present or not. And these patterns are not going to be human designed, but they are going to be designed by the computer. And that is the whole idea behind a convolution neural network. So I'm going to kind of, and this is just an example, that I will make a beak detector, which is a pattern detector, and I will try to take this pattern and check whether it is yes or no in the original image. Similarly, I can have a tail detector, and I can say whether such a pattern is present or absent. So if large number of such patterns are present, I can identify it as a bird. It's kind of the idea, and it's a very simple idea, but it's the idea behind what a convolution neural network is. So, so given enough such detectors or patterns, we should be able to identify whether it is a bird or not. Okay, moving forward. So we can use this, and we can represent a small region with a fewer parameters, and I'll tell you more about it. So another advantage of developing of using patterns is that the patterns that I'm going to develop are going to be position invariant, which means the same pattern appear in different places, so they can be compressed. So what I mean by this is, for example, suppose I have a beak detector. So the beak detector, this is yes means 1. Similarly, upper left beak detector. And once I have this beak detector, once I have, this one, I can also use it in different place. I can use it in a different place, middle beak detector. So as long as the same pattern is present, it doesn't matter whether it is present here or whether it is present in this part of the image, it is still a beak detector. And it's kind of an idea that if you get this idea, then it's going to be easy for you to understand. So they can be compressed to the same number of parameters, and we can use them to identify. So again, a beak detector is an example of a filter, and we call it a filter, and we will use such filters. And filters can be used to identify patterns in the original image. So a CNN, or a convolution neural network, is a neural network with some convolution layers, and we are going to talk about what are convolution layers. A convolution layer has a number of filters that does convolution operation, and we haven't talked about what is a convolution operation, but we have filters. Hopefully, all of you will learn to identify or will know what is a filter. Now, the thing to note is the filters are machine generated. They are not human designed. A lot of people ask me this question. So these are machine generated filters. Now, although I said beak detector, but generally these filters are not human interpretable. So these are machine generated, and the machine generates its own filters that it is using to identify objects. So they are not human generated, which is a very important thing to understand. They are machine generated, not human generated. So later on, some people ask me this question, that what feature detectors did the program use, and they are not supposed to be human interpreted. They are supposed to be machine generated and machine interpreted. So unfortunately, if you try to look at what are the uh, filters that were used, they are actually machine generated and machine interpreted. They are not human interpreted. Again, okay, let's move forward and let me talk to you about what is a convolution operation. Convolution operation is a very simple idea. Let me tell you what it means. So suppose that this is a 6 by 6 image. So this is the original image, and you can, work with me and you can see that this is the original image. Maybe this is a dog or a cat or a bird or whatever. Now suppose there are two filters, filter 1, filter 2. I want to check whether filter 1 is present in this image. To remind everybody, a filter is nothing but a small pattern. So if I ask you this question, is this filter or is this pattern present in this original image? What will be your answer? So can you tell me whether this is present in this original image? Anybody want to answer? Well, yes, it is present. I mean, I can see that it is present over here, and it may be present over here. It's a 3 by 3, so I can, probably look at it. So ones are important. The zeros and minus ones are not important, but again, that's the whole idea. So, and then whether this pattern is present or not, it is present right here. You can see this very clearly. So what we will do is, but again, it's not manual that human eyes are not going to do it. The machine is going to try to identify it. So how does the machine identify a pattern in the original image? The answer is convolution. So next I will talk to you about what is convolution, and the convolution is this. So you take this filter, which is a small pattern, and you start at the top left. You start at the top left, and then you do something called a pairwise dot product. So pairwise multiplication, and if I take this element and multiply by this, and then I take this element, multiply this. So I'm going to do a pairwise multiplication and a pairwise dot product. And can anyone tell me what will be the answer of taking the dot product of this against this? So taking the dot product of this with this. And all of you are scientists, and all of you are highly educated, so you probably have understood what is a dot product between two vectors. So if I do that, I will get the answer 3. Now anyone care to tell us how it will be 3? Well, you should probably know that, 1 into 1, 1 into 1, 1 into 1, and the rest will all be zeros because multiplication by 0. So this will be the answer 3. Now what happens in convolution is, next I start at the top left of the original image. This is the original image, and then after this I move one step to the right. Stride means I move one step to the right, and then I repeat the dot product. And what is the answer if I do the repetition of this? Well, I will get the answer -1. So all of you are very intelligent. It's Mr. Reddy, it is -1 because you can see that this is minus and this one. So the answer will be -1. So again, you can keep repeating this, and it depends on the stride. The stride is how much right you move, and the stride could be two also. It doesn't have to be one, it could be two, like this, and you can keep repeating this process. So generally we will stick with stride equal to 1. In fact, when we do, if we had more time, we would do the coding. And if you have ever done coding of a neural network, there is a hyperparameter called stride, which tells you how much right to move. So again, let us stick with stride equal to 1. So we start at the top left, and then we take the dot product of this with the filter. And so we get 3, and then we have stride 1, and we get -1, and then we move one more to the right. Now, can somebody tell me what will be the answer of the dot product of this with this? So you can simply take the dot product and you can say, okay, what will be the answer? Okay, so you can see this, and then we move further, and then we take the dot product again. And once we have reached the right, we move lower, and then we take the dot product again, we take the dot product, and we repeat this whole process. Now, this is the result of the dot products. So this is the result. Now, you can very clearly see that there are two large numbers, this and this. So the rest are all small numbers. So these can actually be ignored. They are very small numbers, negative numbers. They have no meaning. So there are only two things that are important. So this is this, which means this position, this start, and this start. So these are the only two positions that are important, and this corresponds to this corresponds to this right here. So there are only two things that are important, and that means there are only two matches that are significant matches. So you can easily see that this pattern appears here and this pattern appears here. So by a convolution, so if I want to put it in simple English, convolution is simply detecting the pattern. So detect the pattern. Detect pattern using dot product. And if you are able to understand this simple thing, then you have probably understood a very important part of what a convolution neural network is. So you keep doing this, and this is this. So this is filter 1. So we have seen filter 1 has two significant matches. Now you can repeat the same thing for filter 2. What do we do for filter 2? This is filter 2. Filter 2 is looking for this pattern. These are all not significant. So we are looking for this pattern. Now you can do the same thing and you can see, okay, take the dot product of this filter with this, you get a -1. And then you do the same thing again, this thing. So where is the large number? The large number is here. And what does this correspond to? This location in the original image. Remember, this is the original image. So again, I can see that the filter 2 is present at this location in the original image. And that is kind of the idea behind convolution. Nothing special. I mean, you can see this thing. Now, this is how we do it. So in this example, we used two filters. Now, the important question that you should be thinking in your mind, being all of you are scientists and professors and highly educated people, you should be asking yourself that by using this filters and by using this convolution operation, am I saving the number of parameters? By saving, I mean, am I reducing the number of parameters? So the next point of my presentation is to tell you that by using filters and convolution, I'm saving or reducing the number of parameters. I will be reducing the number of parameters significantly, and I will tell you how that happens. So this output is also called feature map, by the way. Now let's see, and again, if you have um, multiple images, for example, if you have RGB image, I talked about a 1920 by 1080 image. And generally, if you have and some of you may be expert in image processing, the image can be of three types. It could be black and white image. In black and white image, the pixel is either 0 or 1, or 1 or 0. 1 means white, 0 means black. So this is the first type of image, which is black and white. The second type of image is what we call the grayscale image. And in the grayscale image, each pixel can be a number between 0 to 255. So each pixel can be 0 to 255. The third type of image, which is the most common type of image, is called color image. And in a color image, each pixel has three dimensions. And what are the three dimensions of a color image pixel? So this is each pixel I'm talking about. Each pixel. So in a color image, each pixel has three dimensions. Can you tell me what are the three dimensions of a color pixel, color image? Okay. Mr. Srinivas Reddy is again right. There is one dimension for R, one dimension for G, and one dimension for B. And each number is between what range? There are three numbers here. They are in what range? Okay, 0 to 255 again, RGB. So these are the three type of images that you can encounter, and we can have patterns for each three of them. So it's all about building patterns that we can use to identify the images. So this is the important thing. Now comes the most important question for you is how do we save on the number of parameters in a fully connected? Fully connected is what we discussed earlier versus convolution. So if we are doing convolution versus fully connected, what is the reduction in the number of parameters? Because that is what we want. We want reduction in the number of parameters. Earlier in a fully connected, we had about 200 million connections, which was way too many for us to train. So 200 million was, too large. So we want to reduce that. So here is what we do actually. So, this is to give you an idea. This is, to make it simple for you to understand. What really happens is, suppose this is a 6 by 6 image. So this is a 6 by 6 image. Now, what really happens is you take this 6 by 6 image and you flatten it out. So one of the things is neural networks only understand 1D input. So you have to take this image and you have to flatten it out. So see this 100. How did you get this 100? 100, this one and this one. And then this becomes 1. At position 8, there is 1 like this. And then you have the whole thing like this. So this is called flattening the image. So you have to flatten the image. It doesn't matter whether it is 3D or whether it is whatever image, you have to flatten the image. So the first thing is to flatten the image. Now, if I ask you how you got this number 3, well, you will see that we got the number 3 by the following process. We said this is the filter, and as you can see, they are color coded. So this color corresponds to this color, this to this color, and this to this color. So this is what I got, and this is the output. But this number was obtained by using this filter, which means the 9 connections to the original image. So you can see that this number was obtained by using these weights, and you can see this is color coded, this is yellow, and this is green right here. You can see these are color coded. This part of the original image. So I used this filter on, or these are the weights. So you can see that this is 1, this is -1, this is -1, the yellow again is -1, and this is 1, and this is -1. So hopefully this is clear. And I got the answer 3. Now you can say, how did you get -1? Well, I got the -1 by using the same weights. So I did not change the weights. The weights will remain the same. I used the same weights and I just moved them down by 1. So I obtained this -1 by 0. So this connection, and it will be very clear to you in the next slide, this connection was simply moved down by 1. This remains 1. This is 1. This is also 1. The red is -1, and it is also -1. And this is -1 here, this one, and this is also -1. So I obtained the next result by taking the same weights and simply moving them down by 1. And how did I obtain -3? Well, by using the same weights and just moving them down by 1. Now, if you are paying attention, you would see that we are having much fewer parameters and we are doing something called weight sharing. So if you are able to understand this fact, then it will be very easy for you going forward to understand the next concept. Because what is a filter? In the filter is 3 by 3, which is only 9 weights. And these 9 weights are being used over and over again. So I am not really uh, changing the weights or anything. I'm not doing anything else. I'm using the same, that is called weight sharing. And so one filter has 9 weights, and that is it. There are 9 weights. Now let me ask you a question. Suppose I want to use, in the image, I want to use 10 filters of size 3 by 3. Then how many total weights would I have? So one filter has 9 weights, like I told you here. So yes, Mr. Jinesh. Somebody wants to answer this question, that if I have 10 filters of size 3 by 3, then how many parameters would I need? Only 90, right? So good answer. I would have only requirement for 90 parameters, irrespective of the size of the image. So the image size could be 1920 by 1080 or whatever. Now imagine that, suppose 10 patterns may be low. Suppose I want 100 patterns. So if I want to have 100 patterns or 100 filters, each pattern is nothing but a filter. So suppose I want to use 100 patterns, 100 filters, then it's only 100 multiplied by 9, which is 900. So I would only require 900 patterns or 900 parameters, and I would be able to detect 100 patterns. Even if you want to detect 1,000 small patterns, it is simply 9,000. Now compare 9,000 versus 200 million. This is where the advantage lies, and this is what I would like you to realize, that even if you want to detect 1,000 patterns in the original image of size 3 by 3, then you just have 9,000 parameters to worry about, which is nothing, which is compared to 200 million. Now somebody could say, well, 3 by 3 is too small, I want to detect 10 by 10 patterns. Okay, 10 by 10 patterns means you want to have 10 by 10 filter, which means each one will have 100 parameters. So each one will have 100 parameters. Now if you want to detect 100 such patterns of size 10 by 10, so it is 100 into 100. 100 into 100, which means 100,000, which is still nothing as compared to 200 million. Now this is where you have to really think for a few moments, that why it is like that, and why we have achieved such a big savings in the number of parameters. So that is the important thing, and that is the heart of convolution neural network, is we are saving lot of parameters, and we are saving lot of computation time, and we can apply this model to do lot of things for us. We can take an image. In fact, if you look at these days there are image identifiers that identify a person, that identify objects. So all of them use some sort of a convolution neural network to do that. So that is the idea, and I hope I was able to convince to you this. Now generally what happens is, it is not one layer of convolution and one layer is all that we need. We generally have multiple layers of convolution. So if you talk about a convolution neural network, you will see that in practice, and if we have more time, I know we are like, we are close to the end, but if we had more time, we would do coding also, and we would see that in a practical convolution neural network, there is a convolution layer, and then it is followed by something called max pooling layer. I will tell you what is max pooling. So this is this, and then you add one more convolution max pooling, convolution max pooling. At the end of this, you have to flatten everything out, and then you can use it to make a cat, dog, or whatever prediction. This is the original image, and you can take this original image and you can learn to identify whether it is a cat, dog, etc., etc. So let us see something called max pooling. Max pooling can further reduce the number of parameters. Now, let me give you the idea behind max pooling, and then we will see how that even helps us even more. Now, what happens in, you probably know this, that original image, we take the original image and we do the filter on it, we do the convolution with the filter, and we get the output. So, this is the output. Similarly, the original image, you have the convolution 2. This is also convolution. You do the convolution and you get the second output. Now, my question to you is, to understand max pooling, you have to ask yourself which of these numbers is significant in the output. Well, as we saw earlier, only the large numbers are significant. Do I really need to carry this small number or this number along or this number along? The answer is, you probably don't need to carry small numbers around. This means that there is no significant match. So it's like, you don't have to carry this thing around further. So what many people try to do is they try to simplify their output by doing something called max pooling. Now, what is max pooling? It is simply, take the output and divide it into 2 by 2 windows, and then take this 2 by 2 window, 2 by 2 window, and then in each window take the max value. Just keep the max value. Don't worry about the small values. So what happens in the max pooling is, this is a 2 by 2 window, and if I say just keep the largest number, so you will say, okay, just keep this number. In the second 2 by 2 window, what is the biggest number? What is the biggest number? This. So again, max pooling is simply, in the result, simply keep the max number. And basically that is what happens in the max pooling operation. And this is further able to help us because we take this output and then we take this and we give it to the next convolution layer. So by that, it is able to detect patterns within patterns and within patterns, and it really helps us much. So this is also known as subsampling. This operation, if you are familiar with image processing, it is also called subsampling. So basically what we are doing is we are taking this window and we are saying what is the strongest color. This window, maybe it is a 2 by 2 or whatever, 10 by 10, take the strongest color, take the strongest color. And by this, we have subsampled the image to a smaller image, and we have not lost anything. We have not lost clarity or not lost anything, but we have, this is called subsampling, and that is what max pooling is. So max pooling reduces the size of the image without sacrificing quality or any such thing. So this is the subsampling operation, and as I told you that in reality, convolution is followed by max pooling, is followed by convolution, is followed by max pooling, and it keeps on happening. And that is how we, and this is the kind of the important summary, because a convolution neural network compresses a fully connected network by reducing the number of connections and by sharing the weight on the edges, as I showed you earlier. And max pooling further reduces the complexity. And so by doing max pooling, and we do this and we do this number of time, take the image, convolution, max pooling. So this is what we get. And we can keep doing this thing multiple times, and this will detect patterns for us, very fine patterns we can detect. And we don't have to uh, have it human understandable. One of the problems is that the patterns, people ask me this question, that can you tell me which pattern the original image is looking for. So unfortunately, the patterns are machine generated, they are not human generated. But this is the idea. So you can repeat this many times, and you get a new image. And at the end of this, you also further flatten your image, and then you use it, like a traditional neural network. So you add a traditional neural network at the end of it, and you use that to identify whether it is a cat or a dog. You use this thing, and this can lead to very powerful neural networks. If you have never tried it, I highly encourage people to use tools like TensorFlow or PyTorch, because these are the Python libraries that have CNN built in them. So all you have to do is specify the size of the filter, and you have to specify the number of filters and how many layers you want, and it is going to be able to do a very good job for you. So, that is the whole idea. And as you, I mean, I don't know if we don't have enough time, we are almost to the end of the lecture. I would like to leave some time for Q&A, question and answer. So Miss Soumya is asking for a little bit of a coding. So if you are coding in Keras is part of the library for TensorFlow. Then all you have to do in TensorFlow in Keras, if you are using the Keras library of TensorFlow, is you have to specify something like this. Now, this line of code carries a lot of information. If I can tell you what is this line of code trying to do. So can anybody tell me what this line of code is trying to do? Now this line of code is saying that the input size is 28 by 28. That is the size of the original image. 28 by 28. 1 means the number of layers. 1 means it is not a RGB image, it is a black and white image. So this means it is either a black and white or it is a grayscale image. So when I do this thing, so when I give this code, the machine will expect that it will expect a 28 by 28 image of 1. 1 is the number of number of the layers in the input image, which means it is going to be one layer in the input. And 25 3 by 3, what does that mean? This means that there will be 25 filters of size 3 by 3. This is what this line of code means. So in one line of code in TensorFlow Keras, you have specified a lot of things. Okay. So with this line of code, you have told it a lot of things. And then the next line of code this is the input shape, 28 by 28 pixel. 1 means black and white image. If this number was 3, it would mean an RGB image. And then you can, this is how you specify the convolution if you're doing the coding. And then you can do, after doing convolution, you can add a max pooling 2 by 2. Now, what does that mean? That means that you look for a 2 by 2 window, and in the 2 by 2 window you take the maximum and just you take convert this into just 1 by using the max of a 2 by 2 window. You take the max and you get just 1, and you don't have to use 2 by 2. 2 by 2 is a hyperparameter. You can specify what you want. So this is what it will give you. So again, coding is very simple if you are using a library like TensorFlow, Keras, or PyTorch. It is going to become very, very simple. It's not difficult. In fact, we teach that to our students here very simply, and they are able to understand and appreciate it. So by using all of this, you can actually, solve the problem of identifying objects in an image, and you can do that very simply. So again, this is the code, and you can see what the code is doing, and you can see that the number of parameters, again, you have the presentation and you can go through the calculation of the number of parameters. And you can see that we are not going to run into hundred of millions. We are going to just be um, in hundreds or thousands of parameters. So it's all about saving the number of parameters and still being able to identify it. Now, convolution neural network are used many places. For example, they are used even for in a game of AlphaGo or in any game that you are playing. So you can use it to identify the position of the pieces, and then you can use it to predict the next move. It doesn't have to be identifying dog, cat. It could be using to predict the next move in AlphaGo. I mean, that could be another example. Um, and I have seen it, that I have seen, again, this is an example of how we can use this to play games, to identify objects and identifying the screen, and we can use it to play games. We can do all that, and you can see everything is mentioned over here. Similarly, we can use it for speech recognition. We can use it for identifying parts of the images. Scientists use it for example, they use, spectrometry. They use, images. They use spectrometry. They use this thing. They use it in a lot of places. It is used. In fact, when you are detecting some sort of a pattern spectrometry, or if you have some any image, earthquake images, wherever you want automated detection of patterns and images, you could use that. Now people are also using it for text analysis, because they take the text and they convert it into some sort of embedding matrix. And so wherever you can take the text and convert it into some sort of embedding matrix, and then you can use convolution for text classification, whether it is a positive, negative, or whether it is something else. So convolution neural networks are finding applications almost everywhere, and they are one of the powerful tools out there. So I would like you guys to uh, understand and appreciate what a convolution neural network can do for you. It can do a lot of things for you. And if you have never tried it, I highly encourage you guys to look at certain libraries like TensorFlow, PyTorch, etc. That will make coding very easy for you. Now, I would like to take any questions that you guys may have. So, to wrap it up, we can take any questions.
Dear participants, we are requested to ask your questions to Dr. Nagar sir. He is ready to answer your questions. Any questions from participants?
Okay,
Dear
we have
participants,
a question that can we represent image using the CNN output? Now, the CNN output, of course, you can represent the image, but the output would be the result of the CNN operation. So if I ask you what is the output of a CNN operation, it will be like I showed you. So we can represent, that's a very good question, and we can use it. That can be used for image compression. You are right that Dr. C. Kellins Christiana is asking a very nice question, that we can actually represent the compressed image by the output of the CNN. So yeah, that is a very good point. We can use the output of the CNN to represent the same image in a compressed format. but we also need to be aware of the filters. So if you have the filters, you can use that as an image compression, and that's a very good point. Yeah.
Sir, I have one doubt. The
Yes.
CNN networks can be used to identify the small variation in the color patterns or color variations.
Okay. Can we use CNN to identify color variation?
Variations.
Yeah. So what happens is, suppose you have two images and they are different colors, they have different color variation. So first of all, since we are talking about colored images, they will have three layers. The input will have three layers. So yeah, I mean, if the output of CNN is different for the two images, then you will have different outputs, and you can compare the outputs, like the earlier question, to see whether the images have different colors or color patterns are different. Yeah, you can do that.
Any questions? Then shall we close this session? Any questions from participants or close this session?
Good evening, sir.
Good evening.
Sir, the number of layers, how many layers can we add in the CNN? What is there any limit for that?
Okay, that's a good question. As a designer, as a machine learning scientist, um, yes, it is your responsibility to define the number of layers. It's like you can add more layers, you can add less layers. It is totally your call how many layers to add. It's a hyperparameter decision, it's a design decision. So if you add more layers, you probably will have more hyperparameters, but that's the difference.
Hello, sir. Anjali, maybe just put a question in the chat box, sir. Can you tell the major difference between CNN and YOLO models?
Well, YOLO stands for you only look once. I think that's what you are talking about, YOLO models. And YOLO models means you only look once. It's a single stage detector. Both of them are used to identify models. They're different things. They are, you have to look at them in a different way. So YOLO means you only look once, which is you look once and you identify that. And CNNs are more traditional models. So YOLO is like a single stage detector, which means it has less number of layers. It can do identification and classification in a single step. So for that, I think YOLO has less number of layers. That's the major difference.
Any more questions from audience participants?
Once again, sir, the CNN architecture depends on the input what we are giving, like we have seen VGG 16 and all.
Yes, of course. Yes, it depends on the input, and the input, of course, if you have a different input, it will have a different structure. So as I said, it depends on the structure, and it also depends on the number of filters and number of the type of filters that you are having.
Any more questions? And shall we close this session?
Okay, thank you so much, everybody, and thank you so
Thank you,
much
sir.
for
I will,
listening.
then we come to the end of day 2, session 3 of this faculty development program. And on behalf of Department of Computer Science and Engineering of SRM Institute of Science and Technology, Ramapuram, Chennai, I extend the vote of thanks at the conclusion of this highly engaging and informative session on convolutional neural networks and visual data processing. I extend our deepest gratitude to our esteemed resource person, Dr. Anurag Nagar, sir, for sharing his expertise on this cutting edge topic. Your comprehensive explanation of CNNs and their application to visual data processing has provided us with a clear understanding of the underlying concepts, challenges, and real-world application of these transformative technologies. Sir, your ability to simplify the complex algorithm and connect them with the practical use cases are truly remarkable. Your insights have not only deepened our knowledge but also inspired us to explore further and apply this technique in our research and professional projects. And also want to thank the participants for their efforts and enthusiasm which have contributed to the success of this session. To conclude, I once again express our heartfelt thanks to Dr. Anurag Nagar sir for his invaluable contribution to this program. We look forward to more such enlightening sessions from you in this future, sir. Thank you so much, sir. And all the participants are requested to stay connected for the next session, so to be handled by Mr. Sundar Ramamurthy, Principal Data Analytics from Verizon, Chennai, Tamil Nadu. Thank you. Thank you so much, sir.
Thank you. Thank you. Bye-bye.
Thank you, sir. Sir, make me as a host and leave the session, sir.